All right, it says 8:30, so I'm going to start off the conference. I gather I've got three main duties in the next 10 minutes. One of which is to bring everybody in from the coffee. That's the most important thing I'm going to be about to do. I'll show off the Julia jacket. So that's the second important duty. I love this jacket. And these are my badges from the various JuliaCons, 1, 2, and 3, the last 3 years. I'll say a few remarks, and then I'll introduce our first keynote speaker. So let me welcome you all here to MIT, my home. And I'm glad to have everybody here to attend JuliaCon. So people are just still coming in. Come on, grab a seat. Lots of seats in the front, lots of seats over here. Okay, so let me officially welcome you all to JuliaCon 2016. Just a couple of quick fun remarks before I introduce our keynote speaker. So a couple of years ago, we put this blog online, Why We Created Julia. Some of you have read all the things that we wanted. And just a few days ago, Stefan Karpinski was saying that, it's really nice to have a diagram of everything you write. It's, if you write a paper, it's always good to have, everybody wants to see pictures. But how are you going to put all of these things into a diagram? Stefan was saying that it would be completely impossible. And I took the challenge. And so here's my version of the diagram of that first blog. Okay. So I'll leave that up for a second. So I'm going to do a few thank yous of the various folks who've helped out either with Julia or JuliaCon, or there's really too many people to thank. In some sense, this is sort of the general thank you to everybody here, but I also wanted to thank a few folks in particular. With my MIT professor hat on, I wanted to thank the X-Data program for funding the folks here at MIT. There's Wade Shen, who is the leader of X-Data, who's had a lot of vision, believing in Julia. I also wanted to thank the Moore Foundation that's supporting Julia Computing with our endeavors to get to 1.0. So Carly Strasher is going to have a chance to address us all, I think, tomorrow. Another person I'd like to thank is, well, Intel in general for so many things, and Tim Mattson, who leads the Intel Science and Technology Center for Big Data, which also funds us here at MIT and has been very supportive. And then there's the JuliaCon sponsors, which you've seen on the posters, so you probably know who they are, but I wanted to publicly thank them as well. And then there's, of course, the entire committee that's put everything here together. Again, you probably know who they are. So for me personally, Andreas Nowak has been running around like crazy, not only this year, but also last year's JuliaCon. And he's done an amazing job, as has everybody else. My assistant Shirley, who's out front, who you've probably met, and all of you, all of you who've contributed to Julia. It's just a wonderful thing to see happen. Okay, and with that, is there? Oh, there you are. Okay, good. So. That took less than 5 minutes, so what else can I say? Should we get started anyway? All right, so let me introduce our first keynote speaker, who's Guy Steele. I first learned, you probably didn't know this, but I first learned of you and your work when I was at Thinking Machines. When I was a graduate student here at MIT, I used to moonlight over at Thinking Machines, and that was the first time I learned about parallel computing. The year must have been something like 1988, and I learned about these languages called Star-Lisp and C-Star. And I learned so much about parallel computing, many things, many lessons that I still think are some of the best ways of using parallel computers to date. And many lessons I thought had been lost, but I sort of kept them somewhere in my mind at least, and so did some others. Guy Steele here was very much responsible for a lot of the great things in Star Lisp and C Star. I wrote a little cheat sheet here, but just in case I forgot. But so Guy's a graduate of Harvard in 1975. He graduated right here from MIT in computer science in 1980. There are a few of us Julia folks who have a pedigree something like that as well. You know who you are. He was a Sun Fellow in 2003, which I guess is when you started on Fortress, which all of these languages, in one way or another, have had influence on Julia. So Julia is sort of this funny thing that learn lessons from Lisp and learn lessons from the high-performance computing numerical world and sort of kind of put it all together, as many of you know. So the one big lesson that you know, but not everybody knows, is that computer language matters, right? I mean, if you're here, you must realize that computer language matters. Sometimes I talk to my colleagues, they'll tell you that algorithms matter. They do. Mathematical thinking matters. It does. Language matters. Not everybody realizes just how important it is, but my guess is you were probably born knowing that computer language matters because you've been doing it for so long. So without further ado, let me officially introduce Guy Steele, who will give our first keynote talk about lessons learned from Fortress.
Thank you. All set? Oh, good. Well, so I've been invited to talk here about what we learned from a failed programming language project, or at least one that did not receive all of its intended funding. Briefly put, Fortress was an idea that came in 2003 when actually 5 different companies were involved with a DARPA competitive procurement thing for high productivity computing systems. And they said, think of your craziest language ideas that you think might improve programmer productivity in 10 years. And really don't hold back. So we thought of 20 crazy ideas and mixed them together and came up with Fortress. And after a year, those 5 companies were whittled down to 3, and they got another 3 years funding. And after those 3 years, those 3 companies were whittled down to at most 2. That was sort of the part of the outline of the program. And surprise, surprise, IBM and Cray got funded and Sun did not. So our funding got cut off at that point, and we continued to work on the language until about 2012. But it was a language that had been designed to require an implementation team of about 20 people, and we never got funded at that level. We had about 6 for a number of years. And so we struggled trying to implement Fortress on the JVM, and there's still an open source package out there on the internet. You can load it up and run it, and it will run on a JVM. But we never did get to build the real VM that we had envisioned for this language. We never got to do a bunch of other stuff. But we did get to do some fun stuff. And so I think we learned some lessons, and that's what I want to talk about today in doing this inquiry. We thought of 20 crazy ideas. I'm going to talk about 4 or 5 of them today that we thought panned out a little better. So I'm going to start for just a few minutes by talking about my favorite toy programming problem. And perhaps you've seen me give this at the beginning of other talks, but I assure you this talk will diverge in about 4 minutes. Okay, so in this toy programming problem, we're given an array of integers. And we're to regard this array of integers as specifying a bar chart, a histogram kind of thing. So here's the bar chart. And now we do another metaphorical shift and regard the bar chart as terrain and let it rain on it. And the question is, how much water will it hold? Okay, cute little problem. Used to be on one of Google's employment interview exams. This is one of the things they would trot out. How would you solve this? Okay, well, the key insight is that if you can compute the amount of water on each bar individually and figure out how much that is, and all you have to do is add them up. So how can you compute the water on each bar? Well, the next key insight is that what you need to do is look to your left and look to your right and see what's the highest thing on either side. And the lower of those two is going to limit how much water you can hold, because otherwise it'll spill off on the lower side. And then from that lower limit, you subtract the height of the bar you're sitting on top, and that's the amount of water you got. Okay, so essentially, for each bar, you need to look at all the stuff on the left and all the stuff on the right. That means we're having to look at all the prefixes and all the suffixes of the array. And this is a familiar idiom. It is prefix and suffix, but using the max operator instead of the plus operator. So here's a concise one-liner solution in Fortress. Given a list X of 32-bit integers, we're going to return a 32-bit integer. We call it histogram water. And essentially, it is a big sum of taking a left value and a right value, taking the smaller of those and subtracting v, which is the height of the bar. Now, where do left, right, and v come from? Well, what we do is we take the vector x and its max prefix and its max suffix, zip them up, which effectively transposes it from a list of 3 arrays to an array of 3 lists, and then for each v left and right in those, we do this computation. Okay, so this is a purely functional solution. It's clearly amenable to map-reduce style parallelism. We're going to be talking more about that later, because once you computed the max prefix and max suffix, and in fact we have parallel algorithms for that as well, once you zip them up, and you do that lazily or virtually, then the body of the summation can be computed massively in parallel. That part is embarrassingly parallel. And then you add them up, and we know parallel ways to do that. Okay, if you're interested in this problem some more, there's a whole 1-hour talk about this. I did it as a Google Tech talk back in December. It's called 4 Solutions to a Trivial Problem. You can find that on YouTube. Enough about that. But it gives you an idea, it gives you a simple fragment of what Fortress looks like and sort of how it was intended to be used. So we had 3 design principles, sort of meta principles for designing Fortress. We wanted it to be a growable language. So we tried to put as much as possible in libraries rather than building it in the compiler. We wanted it to be a mathematical language, and you've seen the flavor of that, and we wanted it to be a highly parallel language. And we tried very hard to avoid including any language feature not clearly justified by one or more of these principles. So, by growability, we wanted a highly user-extensible language. So, modular libraries, we had a component system with specifically declared APIs, a separate compilation system. We wanted to be able to have multiple coexisting implementations of the same interface. So I've got an interface like array. I want to be able to implement array 100 different ways, and then to be able to select either statically at runtime or dynamically, like statically at compile time or dynamically at runtime, the appropriate implementation array to use in a particular situation. On the other hand, we thought that Fortran, and of course the name Fortress is a play on that. The idea was Fortran, but with some security features and robustness features added. We wanted to break with the emphasis on arrays. We decided to make Fortress an object-oriented language. We would then use the objects to implement the arrays and a whole bunch of other aggregate structures as well. We chose objects with multiple inheritance of traits. Traits are like classes, except you can inherit from more than one of them. Why inheritance? Because we want to share code. Why multiple inheritance? Because we wanted to share even more code, essentially. And then on top of that, to build a distributed and hierarchical implementation of arrays. Therefore, we wanted objects with multi-methods. So you can have many methods in the same object, all with the same name, and you do a dispatch according to the types of the arguments to figure out which sub-implementation you want. And therefore, we needed a mechanism with type-directed dispatch on multiple arguments. This led us into swamps, as I will discuss later. We had some paradigmatic examples. We wanted to have an extensible numerical hierarchy. We wanted to be able to support integers and floats in lots of different sizes, including indefinitely big. So we wanted true integer to be a type language, just as we had big nums in Lisp. We wanted to support rationals and complexes and quaternions and octonions, whatever algebraic structures you might want to support. We were very much interested in interval arithmetic, because at that time Bill Walster was working very hard to develop an interval solver, a nonlinear interval solver. And that didn't pan out as well as we had hoped, because it turned out that keeping those intervals constrained was difficult, but he had a good shot at it, and if he was going to do that, we wanted a language that would support that. Wanted to support vectors, matrices, and tensors, various kinds of collections, including multisets and maps, various kinds of arrays. But the point is, we want to support a broad variety of data structures without having to build them ahead of time into the language, and to allow multiple implementations of the same interface, possibly with different performance characteristics, and let them coexist within the same program. Different parts of a program can use different implementations of multiset, for example. This led us to support user-defined operator overloading. This is included, partly to reflect mathematical usage and tradition. Now, it must be admitted that mathematical usage and tradition itself was not necessarily designed with programming in mind. So you have to apply a little bit of filter there. There are parts of the mathematical language that were sort of not well thought out for programming purposes. One is that the binding and scope of variables was not very well thought out in mathematical notation up to about 1950. And so you have to be careful what you do. And so Fortress was a blend of sort of the best ideas of organizing programs from programming, but also the notation from mathematics. Now, the other reason we wanted to include operator overloading is that we had all had, the designers had a bad experience with big integer and big decimal in the Java programming language. There are things that behave just like ordinary ints and floats, but you can't use plus signs on them. You have to say x.add open b close, and it's just terrible. It's all over the code. Now, the reason you can't do it in Java is because Gosling had a bad experience in C++ with operator overloading, where the operator overloading got abused, and plus got used for, concatenating strings, and shifts got used for doing I/O, and so that's why Java doesn't have it, which why Fortress does. And the thing about operator overloading is that mathematicians had the good taste to overload plus and times and so forth in ways that preserved expectations to their algebraic properties. Whereas using a shift operator on I/O does not preserve some of the interesting algebraic properties of the shift operator. So that's why it leads to confusion in C++. Now, growability requires reliability. That's the rest of Fortress. So we decided to have a strong typing system, for better or for worse, rather than a weak or a runtime typing system. Both types and methods may have parameters. So it's a parameterized type system. The arguments to these types may be other types, but they may also be operator names, integers, booleans, physical dimensions, and physical units. We had support for complete theory of keeping track of meters and kilometers and stuff like that. And we also put in a bunch of design by contract features, much of them inspired by Eiffel, so pre and post conditions on the functions and methods, invariants on objects and traits, and these invariants can be inherited, and we'll see the advantage of that. And we built up a rich library of algebraic traits. So for example, when we declare the trait of true integers, indicated here by the blackboard Z, this is only a partial declaration. The trait of integers, among other things, claims that it extends ring of integers using plus and times. It claims that it's a partial order using usual comparison operators. And in fact, it belongs to a bunch of other traits as well. So here are some examples of some of the lower level algebraic traits in our library. The basic one is the trait of binary operator, and it takes as an argument a type T. And T in turn must extend binary operator of T and the O dot, which is the operator symbol that's used abstractly here, and also the operator O dot itself. Now this thing about T extends binary operator T is kind of a self-type idiom. It guarantees that the type you hand a binary operator is in fact the type that's trying to extend binary operator, so this loop closes and everything works out okay. And the gist of binary operator, the body just says, well, in order to be a binary operator, you have to declare a method that implements the binary operator, and it has to take yourself and some other thing of type T. And then from that, we can say, well, you could also have the trait associative. And in order to be associative, first of all, you have to extend binary operator. We're also going to need an equivalence relation using the equality sign. And once we've got that, we can say one of the properties of this trait is that for all A, B, and C, you've got the associative law, the classic associative law from the textbook. Similarly, the commutative law, and so forth and so on. Now, we had a system for checking these properties by unit testing. You could provide test data for each of the kinds of objects you implemented, and then there's a system that would look at this property and say, okay, we'll take the test data and sort of combinatorially run through it and make sure that it checks out. Our hope for the grand and glorious future is that maybe we could do theorem proving and just prove that the properties always hold. By the way, it's not always obvious when you have a user-defined implementation of plus that it will be commutative. And so we wanted to provide some checks on that. Here's a big example of an algebraic trait. We declare the trait of Boolean algebra. And if you're a Boolean algebra, then you're guaranteeing all kinds of things. You've got two different operators that are commutative, associative, and idempotent. They've got identities, they've got complements. And in order to distribute over each other, they obey De Morgan's laws. And an XOR form a ring. All these things you can say. Why do we care about explaining all these algebraic properties? Well, commutativity can help a compiler a little bit. Associativity really helps you with parallelism. We know this. But also knowing things like if you've got idempotent values, this helps you to do short-circuit Boolean operations without having to build it into the compiler. So from idempotence the idempotent shown here actually has to do with A and A equals A. But there's another one which says that A and false is false. That's idempotent values rather than operations. And that means that once you compute a false in a big set of when you're trying to add together a bunch of things, you don't have to worry about all the others, you're done. And so those kinds of things contribute to code optimization. Now, we had a fourth principle in mind in the design of the language, besides the three big ones that I told you earlier, which is symmetry. And we were trying to establish various kinds of symmetries, and one was that wherever possible, order should not matter. Order of declarations within a file should not matter. Order of import declarations should not matter. Instead, if there are conflicts, they should be resolved instead of just taking the last one you saw, the first one you saw. For inheritance, the order of declared parents should not matter. There are a lot of other object-oriented languages with multiple inheritance where the order in which you declare the parents matters, because if there's a conflict about which method you should take, well, it takes the first one you encountered in the inheritance chain. we thought that would be kind of brittle and lead to programming bugs. We thought overload resolution should treat the parameters specially instead of treating the first one specially. So we've got full multi-method dispatch, not the kind of only on the target object dispatch that Java has. And we decided that arguments should not be evaluated in any specific sequential order. Instead, all the arguments to a method can be, in principle, evaluated in any order or in parallel. That's something that a programmer has to watch out for. We did allow order to matter for matching of arguments to parameters. That is, the textual sequence matters. The first thing is the first thing, and the second thing is the second thing. And for tuple construction, because tuples are ordered. And we went back and forth and decided that statement execution in a block would be by default sequential, because that was such a familiar idiom, although we had second thoughts about that at some points. Okay, so here's another implementation of that histogram thing that's a little more fleshed out. And this is a slide that compares it to another reasonably well-known language, Scala. So here's this Fortress code, and it says that in order to compute this histogram, what we're going to do is compute what I call a max cached tree on X. And that just means that we're going to take the array X, form it into a binary tree, and then at every internal node of the tree will contain the max of all the things below it. And that's easily done in a bottom-up pass over that array. Or rather, you can build that tree fairly easily. And then we're going to walk that tree, and walking walks back down the tree. And at every step, it does this thing where it sort of looks to the left, looks to the right, does some maxes, and sort of takes information and passes it down to the other side. And then as you come back, when you reach the leaves at the bottom, which is the second overloaded definition of walk, if you hit a leaf, then you do the left min right max x.val computation, and then subtract x.val, and that gives you the amount of water at that particular leaf. And then as you walk back up the tree, you're going to sum them again. Notice that in the first definition of walk, it calls itself recursively twice as arguments to the plus operator. So there are several opportunities for parallelism here. One is that each of the three arguments to walk can be executed in parallel. That's not very interesting because those arguments are fairly trivial. The compiler will probably choose just to use straight-line sequential code there. But the two arguments to plus are big, hairy computations, and the compiler will find that it's in its interest to parallelize those. And it does this by means of a spawning and work stealing technique. We'll talk a little bit more about that later. Now compare that to the Scala code. It's not all that different except for the font and some of the characters. The structure of the code is very much the same. All the identifiers are the same. So interesting question arises, why use Fortress instead of Scala? Well, for one thing, we've got this great pretty printing. It makes it look like math. But the other reason is that we've got a parallel implementation. The Scala implementation is sequential. Now, the question is, how do you keyboard this mathematical stuff? And that was actually one of the big issues with Fortress, is we wanted the programs to look like math. There's always this question of what does the IDE look like? What do you type on the keyboard in order to get that stuff? So our solution temporarily was we edit in Emacs, but we were just using ASCII code. And there's an ASCII representation for Fortress shown at the bottom of this slide. It doesn't look all that different from the Scala, except in a couple places. And then we had a tool that would then take that and render it onto the screen or on paper as this mathematical stuff. Okay, let's go on from there. So some similarities between Scala and Fortress. Both are object-oriented. They both have traits with multiple inheritance, although the exact treatment of the multiple inheritance differs. Fortress is more symmetrical. Both have overloaded functions and methods with parametric polymorphism of traits, functions, and methods, which means that traits, functions, and methods can also all take type parameters as static arguments, and that affects how they behave. It's expression-based. There's no dichotomy between statements and expressions such as we have in Java or in C. Tuples and tuple types, and you can just write them by writing a bunch of things separated by commas and parentheses. That's a tuple, and it's a first-class type and a first-class object. They both have collection libraries with a heavy functional emphasis with all the usual methods like map, fold, filter, sorted, and zip. Language features to enhance growability, although different perspectives on that. Both of the languages allow Unicode symbols to be used as operators, and you can overload them. The difference there is that Fortress actually uses them. There is a potential, but Scala doesn't actually have a huge library that lets you use an intersection symbol to intersect the sets. So that is built into the Fortress libraries. And finally, the design of both languages is strongly influenced by Haskell. Now, some differences between Scala and Fortress. Fortress types are never erased. All the type information is around at runtime, including all the type parameter information. The dynamic overload dispatch in Fortress is fully symmetric. And type parameters in Fortress, unlike Scala, are often, I say sometimes here, but they're often inferred at runtime. And that's, again, that swamp that I referred to. It turns out that inferring the type parameters at runtime is hard. And I'll talk about that fairly late in the talk. There's implicit as well as explicit parallelism in Fortran. Tuples and binary operators have potentially parallel operands, and argument expressions and calls are potentially parallel. And the syntax of Fortran is strongly influenced by mathematics and whiteboards. We actually used this as a slogan later in the development of Fortran. We want to run your whiteboard. We notice when scientists are just scribbling at their whiteboard, they don't write purely formed Fortran code or C code or Java code or even Julia code. They tend to scribble a mix of mathematics and domain-specific notation and some programming notations. And we said, what if we could get close to that? What if we could get close to that? So the Fortran libraries encourage the use of these symbols and absolute value notation and floor notation and some kinds of two-dimensional notations. And multiplication can be expressed with a center dot or the cross symbol or just by juxtaposition, but not the asterisk. Man, that bugs me. The asterisk was a commercial symbol in the 1950s, and Fortran grabbed it because the key punch did not have anything better. And we've been stuck with that history for 60 years now. So here's a really important resource for a language designer. And it's an often overlooked resource. It's white space. How to use white space effectively in the design of your language syntax so as to enhance readability, to enhance codability, and so forth. Well, here's a good example of how not to do that. In the original Fortran, white space, except in Hollerith constants, that is character strings, did not matter. So here's a do loop that you could write in the original Fortran, way back in the day, or Fortran 66, which is not the original Fortran, but close enough. So here's a do loop. Do, the end of the do loop is at statement 20, I goes from 1 to 125, and you say sum gets sum plus x sub I. Okay, that's clear. But this is also a do loop. You're allowed to squeeze the white space out. And it's the job of the compiler to figure it out. And it turns out that the Fortran parser was really interesting. Okay, now suppose we take that and suppose we change the comma to a period. The first line then becomes a valid assignment statement to a variable called do20i of this constant. That's a perfectly legitimate Fortran statement. And the fact that you've got this other statement out there with a statement label 20 that isn't used is of no concern to the compiler. You can label statements if you want to. Sometimes people just numbered all the statements so that if you drop the deck, rather than putting a sequence number in columns 73 through 80, they just put it in the statement number field. And the programming language BASIC took that to an extreme. You just had to number every statement. Okay, but you can put spaces back in. It turns out that here in this fourth example, that first line is also an assignment statement because the white space doesn't matter. In this case, the compiler will gladly squeeze the white space out of that first variable name, do20i. Okay, this is how not to use white space in a language because it's confusing and misleading. Okay, here are 3 ways in which we used white space in Fortran. One is it turns out that the syntax of the vertical bar is rather delicate because vertical bar gets used in a bunch of ways, both as an infix kind of notation and as a surrounding notation in the absolute value brackets. And so the Fortran parser looks at the white space around the bars and sees whether it's symmetric or not. And so you can write this, the set of the absolute value of A, where A is taken from my list, such that A divides B. And so the vertical bar is being used for absolute value brackets, being used as the divides by predicate, and it's also just being used as part of the set such that then syntax. And what's on the left is the ASCII, and what's on the right is the pretty printed version of that. Another way we chose to use white space is distinguishing subscripts from array constructors. So if between an array A and the left bracket there is no white space, then it's firmly attached. We say it's tightly juxtaposed. We use that as subscripting operation. But if you stick white space in, then they're regarded as 2 separate expressions. And you've got this array, and then you've got this array constructor. And what it means when you juxtapose those two, well, that gets determined by the library. Because juxtaposition is just like any other binary operator. It's user overloadable, and the libraries decide what that means. A third thing we used it for is verifying the intent of operator precedence. So if you write A plus B times C plus D, and don't put in any white space, that's OK. And if you spread them all out, that's OK. And if you decide to keep the multiplication tight and the addition loose, that's OK because that corresponds with the intent of the operator precedence. But this fourth example is rejected, and the compiler says, oh, well, it looks like you intended the multiplication to be looser. But in fact, we know that multiplication has higher precedence than addition. You really don't want to do that. So we're trying to use the white space as a confirmation, not as a dictation of the precedence, but as a confirmation of the precedence, so to help ensure at least a little bit that the use of white space is not confusing. So juxtaposition is an important resource. In Scala, Scala and Fortran take two different approaches to this. And Scala has a very nice system. It's consistent. You can use any name whatsoever as an infix or postfix operator. And the way they make this work is that if you have a bunch of things that are just juxtaposed in order, then they are considered to be operands and operators alternating. So in this, we say x equals item.x, max item.y, max item.z, min upper bound. And the occurrences of max are not variable names. Those are operators because they happen to occur in the even numbered positions in the juxtaposition. Actually, even numbered from the end. It's a little trickier than that. The downside of this approach is that Scala, because of this syntax decision, Scala cannot have any prefix operators other than the 4 built-in ones. So the set of prefix operators is not extensible in Scala. We took a different approach in Fortress. Juxtaposition is a user-defined overloaded operator. It gets used to express both multiplication and function application in the library. And you can write stuff like this, including 3 sine of pi x and minus log x plus 5z squared. It all parses correctly and works. We also experimented using it with a smart string concatenation. And when we finished the project, we decided the jury was still out on that one. So you don't need to use the plus sign to concatenate the strings. You can just write them next to each other. And it makes strings like this, I found n+1 errors in J files, a little more readable, not have all those plus signs there, we thought. One of the tricks that makes that work is that tight juxtaposition is given higher precedence than loose juxtaposition. Those are actually considered 2 different operators. The downside is that operators need to be distinguishable tokens. We can't use lowercase max. Instead, we have to write uppercase max. And so operators have to be in uppercase and variables get done in lowercase in Fortress. Which reminds me, actually, the fact that we've got an alphabet in ASCII with 2 cases is an interesting design resource, and different languages use that in different ways to distinguish variables from types, distinguish variables from constants, things like that. But any language designer should think carefully about how to use that case distinction because it's a scarce design resource. Something I think we did right in Fortress was to have non-transitive operator precedence. Here's this example. It's okay to write a plus b is greater than c plus d. Why is this okay? Because plus has higher precedence than greater than. And that's true in nearly all programming languages nowadays. It's true in C, it's true in PL1, it's true in Fortran. And it's okay to write p is less than 0 or p is greater than 9. 9. Why? Because greater than has higher precedence than or. That's also a very convenient rule. But in all these other languages, that then implies that because their precedence is transitive, that plus has higher precedence than or. And that's not necessarily a good decision. In Fortress, it is not okay to write a plus b or c plus d. The compiler says, you've got these 2 operators next to each other. I don't know what precedence you intended. And in fact, in Fortress, there's no precedence defined between those 2 things. And the solution is parenthesize it to indicate which one you wanted. In Fortress, we used only the most obvious and familiar rules of precedence. Our motto was, if you didn't learn it by the first year of college, you shouldn't be relying on it. So we've got the familiar precedence on between plus and minus and times and divide, between plus and minus, times and divide in the relationals, between the relationals and the Booleans, and the set operators and so forth. Intersection and union are higher than the subset symbol, for example. We don't allow mixing. There's no precedence relationship between plus and intersect, for example. Just not there. This really matters when you have hundreds of operator symbols instead of only about 15 in your language. And all you have to do is use parentheses as shown at the bottom to make your intention clear. We also looked at the issue of assignment versus binding. There's this question of how do you distinguish a binding from a variable from an assignment of a variable. In Scala, there are 2 keywords for declarations, var and val, and then a bare equality sign is used for assignment, as it is in C and Java. We decided to turn that around in Fortress, and we wanted to subtly encourage programmers to think more about static single assignment styles of writing, and to think of assignment as the rare case. So we intentionally chose the simple equality symbol to be a binding of the variable, always. And for assignment, we use the colon equals. Now, there's been a long syntax war, for 50, 60 years, going all the way back to Algol. Should we use equals or colon equals? And in the sequential imperative languages, assignment is more common than declaration, and therefore it makes sense that people would rebel at using colon equals for this very commonly used operation. In Fortress, other aspects of the language were designed to make assignment rare. And so we decided to impose a syntactic tax of 1 character on assignment as compared with declaration. It's good for you. We paid attention to the design of comments. Most programming languages just say, you throw in some symbol and everything from there to the next new line is we don't care what. We decided to care. We wanted to encourage the production of good comments. We wanted to encourage the production of beautifully formatted comments. This is something Knuth does with his literate programming system with web and Tangle and so forth. But we wanted it to just be built into the syntax language itself. So we decided that all Fortress comments would have Wiki Creole syntax. And so you can use italics and boldface and links to URLs, and you can insert images, and there are ways of sticking in drawings and stuff like that. We chose Wiki Creole because it was more verbose than other wiki syntaxes. It was a standard at that time. And that standard is still kicking around. I was hoping they would update it to Wiki Creole 2.0. I think that never happened when I checked as of a couple of weeks ago. But although this syntax consistently uses doubled characters to indicate formatting controls, we chose to use only single backquotes surrounding things for a very specific purpose, which was citing Fortress code in the comments. So we can say things like, the best way to swap X and Y is this piece of syntax. And by surrounding those little pieces of syntax with single backquotes, you get the effect of the Fortress formatter inside the comment. And so the comments look beautiful in that way. And the reason we did this is because we wanted to encourage programmers to talk about the code in the comments. So we want to be able to stick in code, and we wanted that to be syntactically cheap, therefore only one character instead of two. This may seem like a very trivial bit of design thing, but it's the kind of thing you really need to pay attention to make a language more usable. Frequently used notation should be clear, memorable, and concise. Fortress adopts the Haskell constructor and comprehension notation, but with beautiful syntax. And we made a point of supporting arrays and lists and sets and multi-sets. Fortunately, we were able to break out beyond ASCII, which only has 3 sets of brackets, the parens, the brackets, and the braces. And we were able to use funny curly brackets and all kinds of things. Unicode has, I think, 29 pairs of brackets. And we did not try to use all of them. We knew that 5 or 6 was better than 2 or 3. We also supported big reduction operators, so big sigma, big max, big O plus, that kind of thing. And it turns out that when you focus on the implementation, these reduction operators are semantically identical to comprehensions. They have very different traditional syntaxes. You use comprehensions when you're pretending to build an aggregate structure. You use reductions when you expect to end up with a number or something. But semantically underneath, they're the same thing. Each is controlled by some generator that will generate a bunch of things. Then you map some body expression over those things, and then you reduce them in some way. You combine the things you computed individually to produce a number or a list or something like that. And so our language mechanics for parallelism were focused around primarily taking advantage of the map-reduce structure of comprehensions and big reduction operators. And so we had a very general big operator and comprehension syntax. Again, this is all completely user extensible. The meaning of big sigma is defined in some library somewhere. A big operator syntax, such as big sigma's I goes from 0 to 9 of a sub I x to the I, simply desugars to a method call on some method called big sigma, and it is handed 2 things. It is handed a generator, and 0:9 is in fact a generator that can generate the range of integers from 0 to 9, and a function to be mapped, which simply represents the body, and the parameters of that function are the parameters that are bound in the generator expression. In this case, it's I. And then from there, the implementation of that is in the library. So big sigma turns around and does a callback to the generator and says, I'm going to call your generate method, and I'm going to hand you some specification of my reduction, and also hand you the mapping function. This gives big sigma a chance to step in, and depending on exactly what types are involved, hand different kinds of reduction specifications to the generator. As a result, when you have a big operator or comprehension syntax, what happens is that there can be many implementations of a specific generator, many implementations of the reduction, and they sort of do this dance through the type system to resolve which pair is the appropriate one to use in the situation, and therefore you can optimize them for performance. So that's the goal. And in particular, you can make decisions about whether to be parallel or not. So lots of use of generic types. Generators and reducers are generic in the element type being generated to reduce. Their methods have further generic type parameters. I wish I had time to show you all this code. It's lovely, but it takes pages and pages in the library to explain. Generators can be lazily composed. You can take cross products of generators, so you can generate pairs of things. You can concatenate generators, things like that. And you can code algebraic properties of each in the type system. When big sigma hands a reducer to that range and says, generate these things, and I'll take care of the reducing. I happen to be addition, but you don't know that. But it does tell it, oh, by the way, I happen to be associative. You might want to take advantage of that for parallelism. However, if you're reducing floating point numbers, it might say, well, I'm not really associative, and you might want to be careful about that. And so there's a way to say that I'm mostly associative, and that's all, again, encoded in the libraries. Or I'm approximately associative. On the other hand, floating point addition is purely commutative, so you can claim to do that. And so algebraic properties, which are encoded as static traits in the type system, are used in the overloaded method dispatch of the generator to decide which of several implementations of generator to use so as to match appropriately to the reduction operation in its described algebraic properties. So that's what all that is about. And all this is defined in the library code. The lowest level cooperative parallelism is based on the tuples, the arguments, and binary operators. We've already specified that, mentioned that earlier. The compiler figures out which sub-expressions are worth making into microtasks. That was still an area of research we left off. It had to do with analyzing whether there are recursive calls or potential recursive calls, analyzing the complexity of expressions, and trying to figure out whether a particular sub-expression is big enough to worth spawning as a separate task rather than just going ahead and executing it right there. The microtasks are automatically load balanced during work stealing. And the overall goal is we wanted to do for processors what garbage collection does for memory. What a garbage collector does is relieve you of the worry of deciding exactly what data goes where in the memory, and it kind of takes care of it for you. Now, sometimes it doesn't always do a good job. Sometimes you want to give advice to the garbage collector, that's fine, or the storage manager. We want to do the same thing for processors. Instead of worrying very hard about which computations go on which processors, we'd like an automatic processor manager to take care of that for you. And this approach was our attempt to do that. Now, all this has to do with cooperative parallelism. You got a bunch of processing resources come to bear, and they're all cooperating to do some reduction or some mapping operation or something. But competitive parallelism can also enter into play. You can spawn off two processes, they can start competing for resources, such as access to a shared piece of data or access to some I/O device. So how do you compete for resources with low overhead? We could use locks, but locks are totally pessimistic. You lock and say, I'm going to shut everybody else out even if nobody's banging on the door trying to get in. Alternatively, transactional memory strategies have optimistic strategies for implementation. Therefore, we decided to go for transactional memory, which was still a fairly new kid on the block 13 years ago. And so Fortress provides atomic blocks that appear to execute all at once, and they are implemented using transactional memory semantics. And getting transactional memory operations to nest properly and interact properly with exceptions is interesting. It's still a topic of research. Do the research of that. Okay, now I'd like to talk a little bit about the issues you get into when you have multiple inheritance. Okay, so I'm going to show you a tiny, tiny piece of the Fortress library's type hierarchy. At the very top, we have any. That's slightly different from object. Just to include any also includes functions and other things. But below any, we have strings and booleans and numbers. Numbers can be divided into integrals and floats and a bunch of other things, like quaternions. And there are several integer types, of which I've shown 3, the 32-bit ones, the 64-bit ones, and the truly huge ones. And 2 types of floats, although again, there could be more. Okay, so that's enough for this example here. So the question is, will method overloading work? And suppose we just want to overload the print method, common workhorse tool. So we provide a method for printing strings, a method for printing booleans, and a method for printing the various kinds of integers and floats. And when you just call print with an argument, then a type dispatch happens. And it happens at compile time if the compiler is able to figure it out, and if not at runtime. You look at the type of the argument and say, which of these am I? And I need to go to one of these entry points for the implementation of print. And the compilers, of course, aggregated these entry points and made them defer to each other in the appropriate ways. And by the way, I've shown just print operations for the leaves of the tree, but I also could have an implementation of print that works on all claims to work on all numbers. So there might be overloading at the interior points of the tree, but for my purposes here, just showing the leaves is sufficient. And the problem here is, how do I know there isn't some weird guy out there that claims to be both a string and a boolean? Because I've got multiple inheritance. And so maybe I've got this implementation object that if you ask it boolean-like things, it does and or. But if you ask it to be a string, it'll happily concatenate. And maybe it's boolean, this has to do with whether it's empty or not. That's one possible semantics. But for all we know, somebody implemented an object that inherits from both string and boolean. So when we call print, how do we know which entry point to use? And the answer is there's an ambiguity there. In fact, there's an inherent ambiguity there. And it doesn't have to do with whether such an object actually exists or not. It could exist. And therefore, going back to this previous slide, when the compiler sees this set of things, it'll say, oh, that's an invalid overloading of print, because a method call might be ambiguous if you hand me an object that might be both a string and a boolean. So our motivation for supporting multiple inheritance is we wanted to be able to share code and to share various other kinds of things. But then in such a system, sometimes you need a way to say, I don't want sharing. I guarantee there's no sharing. How do we say that if you're a Boolean, you are definitely not a string? And so we put a syntax into language for that. In a trait, besides saying what we can say that string extends any, we say Boolean extends any, but it also definitely excludes string. And that's a guarantee that no object can implement both Boolean and string. Then we say, well, okay, now we're going to have numbers, and that extends any, and it has to exclude both strings and Booleans. And now we invent this other kind of thing. Maybe we want arrays, and we want arrays not to be strings, Booleans, or numbers. Or maybe we want them to be strings, but not Booleans or numbers. Anyway, the point is we get this quadratic blow-up using this exclude syntax. And when you end up with 20 things, and you want them all to be mutually exclusive, the last guy has to mention the 19 other guys, or you have to make sure that all the exclusion possibilities are covered. That got out of hand. So something we thought of at the last minute, just before the project folded, was a way to annotate their parents and say that certain kinds of traits are considered to be partition traits. And so here's a revised hierarchy where below any we've inserted primitive. We say primitive is a partition trait. And the meaning of a partition trait is that no object can implement more than one of its immediate subtraits. So in fact, it serves as a partition on the things just below it. This turned out to be a fairly nice system on paper. We actually didn't get around to implementing it. But the point is to avoid the quadratic blow-up in the text of the libraries. So that was an interesting idea, and I put it out there in case anybody wants it. Okay. Okay, sort of finally, I'd like to talk about the Fortress method dispatch mechanism. As I've already said, it provided fully symmetric, meaning all the argument positions are treated identically and with equal import, and not favoring one over the other. I want to really emphasize that. Fully symmetric, dynamic, multi-method dispatch using the runtime types or the actual classes of all the arguments. What do I mean by actual class? We actually don't have good terminology for that. For Fortress, we invented the word ilk, which we retronymed as implementation level kind. But really, it is the most specific trait to which it belongs. Of all the different traits that it could claim to be an instance of, the most specific one, which is way down at the leaves of the type hierarchy, that is its ilk. That is sort of what it is. And so when you do the multi-method dispatch, you look at the runtime types, and then you look at all the different method declarations, which, by the way, might have generic type parameters, and try to figure out which ones are applicable, and then among those, which is the most specific. And there are very complicated rules. We've written papers about this, about how you decide which of two parametric methods is the more specific. And we can do this, and part of the motivation for this is there's been no need for visitor patterns. The whole visitor pattern thing, which has been around since the mid-90s, is essentially a trick for getting around asymmetric multi-method dispatch, because you can only dispatch on one thing at a time. And we thought visitor patterns are going to be used extensively in an overloaded library like such as we want to build. We didn't want all that Mickey Mouse is just there because the mechanism is insufficient. So in Fortress, the types are never erased. Therefore, all the type information are at runtime. Therefore, dynamic dispatch can not only distinguish a list from a string, it can also distinguish a list of Booleans from a list of strings, because that type parameter, type argument information is there. And both list of Boolean and list of string are dynamically more specific than just list of type variable. So we can have these three declarations of crunch, and the first and second declarations are considered more specific than the third one. And if Boolean and string mutually exclude each other, then list of Boolean, list and string can also be made to exclude each other, and so forth. So when you have a particular thing, mylist, when you call crunch, it could end up invoking any of the three definitions depending on which one is best. Now, in the general case, it's necessary to compute values for these type parameters as you enter the method, such as t. So if it turns out that mylist, which is declared as a list of objects, actually turns out to be a list of threads, then when you call crunch with mylist, you need to infer at runtime that we're calling the third one. And as we enter that entry point, we need to figure out that t must be thread. Or, yeah, right. And so that's a little thing, and that seems like a trivial thing. Oh, it's a list of threads. The type is right in there. You go in and grab the thread, and now you've got it. But in the general case, methods may have multiple static parameters. Each of the static parameters may have declared bounds that constrain it. And those bounds may depend on all the static parameters, including itself. So we can say things like, here's this method mangle. It's got three static type parameters. And M has to be a partial order and a group using the plus operator, or otherwise I can't implement it. I need the plus operator. And F has to be a function from M's to N's, and N has to be a list of M's. And so when I'm given three random arguments, I've got to figure out, do these three arguments, do their actual types, satisfy this this set of constraints on the type parameters. In fact, what it amounts to is solving a system of type equalities on a domain that is a tangled hierarchy, a tangled heterarchy actually, at runtime. And it turns out that in general, this is very much like the problem of solving a set of simultaneous linear equations. And in the general case, you have to do things like Gaussian elimination to figure out what M and F and N are. Now, there are very interesting special cases that happen most of the time. You can accelerate those. But a lot of the research we were doing between 2010 and 2012 was figuring out how to make this solving of systems of type inequalities at runtime efficient. So, in fact, this is where we got stuck. The interaction of generic methods with a symmetry requirement led to general parametric formulations of what we call the meet rule and the return type rule. The meet rule essentially says that if you have two method declarations which overload each other and neither is more specific than the other, then there must be a third one that is more specific than either of those two. This guarantees lack of ambiguity. There's also a return type rule. The return types of things have to obey the appropriate relationships so that covariance and contravariance is obeyed, essentially. So this requires non-trivial constraint solving at runtime. Non-trivial is a euphemism for, as best we know, exponential cost. We believe in the general case, when you've got contravariance and union types, it turns out they interact badly, and we think the problem may be NP-hard. We were unable to find an algorithm that was better than exponential cost in the fully general case. On the other hand, in practice, nobody nests contravariance or union more than, say, 6 or 12 deep. And so if you're willing to put a limit on it, say, you know, well, after we've crunched on it for half an hour and gone 12 levels deep in recursion, we're just going to give up, that will probably be adequate as a practical matter. So we also discovered you could limit this by imposing a lexical asymmetry on the type parameters and methods and say that instead of letting the bound on each type parameter depend on all the static type parameters, let it depend only on that one and the ones to the left. And that has the effect of guaranteeing that the system of equations is upper triangular. And we know that upper triangular equations can be solved a lot more easily from our experience with linear equations. But it turned out that another nasty case popped up. The return type rule had non-trivial consequences. It would take another hour and a half to explain that, so I'm not going to get into it. But the moral of the story is we had a really grand vision for an extremely general parametric type system with multiple inheritance that was completely symmetric. We had a grand vision, couldn't quite pull it off. And when the plug got pulled on the project because we weren't making progress, we were just beginning to make some breakthroughs on that, but too bad. And now I'm working on machine learning instead of language design. So I'm having fun at Oracle Labs, so I'm not doing Fortress. So I think we learned some good things. To wrap it up, we believe that we learned things about how to implement generic types with multiple inheritance of generic methods and symmetric dynamic dispatch. We learned some good things about expressing parallelism implicit in the language, just saying that the arguments to tuples and binary operators can be done in parallel, and implementing that using automatic work stealing. That turned out to be very expressive for coding libraries of comprehensions and big reduction operators that we use MapReduce strategies to implement them. It allowed a good way of factoring the parallelism, so that in fact, as you did the dynamic dispatch on the big sigma operator, you could decide, is this collection worth parallelizing or not? You know, or should we just do it in the obvious sequential way? And can we take advantage of the algebraic properties of the reducer? We learned a lot about parsing a more mathematical syntax, things about, I really believe this idea that in a good programming language, operator precedence should not be transitive. Transitivity was a bad idea because once you get more than about 3 levels of precedence, it gets confusing. And so that is something I would recommend to any language designer, including the design of Julia. Consider that as a possible retrofit. And the only penalty to the user is if the compiler says, I don't understand this, you just put in parentheses. And I think it guarantees that your code is more readable. We also learned a lot about pretty printing mathematical syntax. This is something I need to write up, but we had this fairly extensive thing that did a great job of indentation, did a great job of figuring out what fonts to put things in, that kind of thing. And we also had an interesting implementation of checking of physical dimensions and units in the context of that generic type system. So you could overload plus, and plus would guarantee that you could add meters and meters. You could even add meters and kilometers. You could not add meters and kilograms. And again, all that was encoded in the libraries. But just a little bit of support in the syntax language provided the facility for doing that. But we got stuck in the swamp of this extremely general type system. And as I say, we were learning about ways to back off and make it more tractable and more implementable. And if I were to do this over again, I would back off and try to exploit a subset of these ideas using a less complex type system and see what I can make of it. Or maybe Julia has eliminated the need to do that. That's fine. I like Julia. So another point about syntax, there are trade-offs between readability and writability. And mathematical syntax, as has been handed down to us over the last several centuries, was designed more for certain kinds of concision than for robustness. It's a great whiteboard language. You want to keep that small. And in particular, simple juxtaposition gets used in a lot of different ways in traditional mathematics. We attempted in Fortran to make this programmable. Sometimes this worked beautifully. Sometimes it required some weird contortions. Sometimes it encouraged us to write code that really wasn't very readable after all, and we had to back off on the use of juxtaposition. Haskell and Scala do their syntax somewhat more consistently, and I think that each captures a certain part of the mathematical tradition quite well. In particular, Haskell covers the traditional functional programming where we use juxtaposition for function application very nicely. Scala uses juxtaposition to allow alternations of expressions and operators and lets you do overloaded binary operators very cleanly. Mashing the two together is trickier. We tried to do that in Fortran, and I think we had only partial success. So I knew that when I started the Fortran project in 2003 that having it actually take market share from either Fortran or Java was a long shot. That was the goal. That was the goal. DARPA wanted us to build a petascale supercomputer. Oh, that seems so quaint now. Now we're working on exascale systems. But back then in 2003, the goal was a petascale system by 2013 that also had a lot of software to support programmer productivity. And our goal was to try to displace Fortran a little bit in the national lab contexts, essentially, who are some of the stakeholders and funders of this thing. On the other hand, yes. Okay, 1 minute. I wanted to assume we were wildly successful, and we proceeded quarterly. We ran into several hard problems, solved some of them, and revised the design over the years. And sometimes I think we revised too much. I think that programming languages have life cycles. Most languages don't thrive forever. On the other hand, many languages don't die completely. And I believe that good ideas survive by hopping from one language to another. And that's part of what I'm trying to do here in this talk. The language Fortran, I think, is dead. Some of the ideas are interesting and may hop to other languages, and I'm trying to spread them a little bit by giving talks like this. Maybe a few ideas from Fortran will prove useful. I think that Apple's Swift has borrowed a teeny little bit of syntax from Fortran, and maybe that's for the better. And I'll leave you with this. Greenspun said in 1993, his 10th rule, he only had a 10th rule, he called it the 10th rule to catch your attention. Any sufficiently complicated C or Fortran program contains an ad hoc, informally specified, bug-ridden, slow implementation of half of Common Lisp. This tells you something about his attitude about Common Lisp as a reasonable set of utilities. Here was one of my mottos. Any sufficiently complicated parallel program contains an ad hoc, informally specified, bug-ridden, slow implementation of something. And I'm out to try to figure out what that something is. And I'm not there yet. And Fortran is one step at that. Thank you. Do you have 2 minutes for questions?
We can take a couple of questions, and I'll ask the speakers to repeat the questions for the microphone.
Okay. Yes, up there.
I'm wondering about your experience with discoverability of traits. So if I'm defining one of the traits that I want to add to it, like associativity.
Yes.
But if I forget, someone will throw an error, which is maybe not running in parallel. So I'm wondering if this was a common practice that you had any way to help you decide what traits you should implement or invite to adopt.
Yeah, and this is a classic problem in the language design of any, I will repeat the question in a second, of any object-oriented language with inheritance. What happens if you forgot to declare that some object should inherit something and you didn't? Can you patch it up after the fact? And are there tools to help you figure out that you should have declared this when you didn't? And no, we had not tackled that. That's a great idea. That's a subject we had not gotten into. Very good point. Way up into that.
So you said at some point that choosing static typing is better or worse. So since you've got a lot of experience on both sides of that choice, can you talk a little bit about the better or worse? Like what was
Yeah.
the worst part?
About the strong typing versus the weak typing. I think there is value in providing types. I think programmers constantly have types in their heads, and I think anything worth telling yourself is worth telling the compiler to help double check you and perhaps to exploit it. On the other hand, making some kinds of typing optional is value. Fortran does provide for type inference, so although it's strongly typed, you don't always have to say the types explicitly. But that's different from actually having weak typing and just letting things kind of be generic until actually push comes to shove when you get to the dispatch. And there you actually look at the types. So there are pros and cons. I was glad we tried strong typing for Fortran because we got a lot of mileage out of declaring this very rich type system. But it's not everybody's cup of tea. I don't feel very strongly that a language must be one way or the other. One more question? Way up in the back.
So how would you describe floating point lack of associativity in your description of algebra?
Yes, the question was how do we describe floating point associativity or lack thereof in the algebra? And for associativity and several other related operations, we had a notion of truly associative and approximately associative. And the difference is that in the equivalence relation, instead of having true equality, we said, well, we'll check within some fuzz for testing purposes, but we know it's sloppy and it's probably the best we can do. So if someone wants it to be truly associative, it'll say, well, I'm not. And if it's approximately associative, then at least the property checking will say, yeah, it's sort of associative. It may be good enough for your purposes, beware. Okay, that's it. Thank you very much.